Chugunov.
Chugunov, also from the Shemyakin-Ovchinnikov Institute from Moscow. He's talking about
Modeling of temperature activation of ion channel TRPV-1 by method of molecular dynamics. Антон, правильно перевел, да? Да, говорю.
Good evening, dear colleagues. As my respect to Mr. Chairman and to several other people in audience who would prefer listening in English, I would try to make my talk in this language. And the topic is temperature-sensitive gating of TRPV-1 channel as probed by atomistic simulation. So this is purely modeling work, and I will tell you a brief story about how I discovered what is TRPV-1 channel. Last summer I had a great trip to Kamchatka, and I have seen wonderful hot springs there, and I entered one of the pools which was extremely hot, and I was wondering what is the temperature of this pool, and I thought it would be about 50 degrees, and after that I took a thermometer and I measured the temperature, and it was 43 degrees Celsius. So this is the temperature of activation of this TRPV-1 channel, and we cannot freely tolerate temperature above this. So the temperature above this threshold would be the level of pain, which is caused by the heat. And in our there are other stimuli that can activate this channel. These are low pH values. These are capsaicin, which is the active compound of hot pepper. And this receptor is characterized structurally. So we know, and both open state and closed state structures, which have been produced by cryo-electron microscopy in David Julius' laboratory and their colleagues probably, but still we do not know exact activation mechanism of this receptor, and in our laboratory of computational modeling in Institute of Bioorganic Chemistry, we set a task to understand which is the mechanism of temperature sensitivity and the path of activation of this receptor. And this work was initiated also in a collaboration with Professor Grishin and other neurobiologists from our institute. There are a lot of data which was done on this receptor. Big biochemistry was done, and many computational works, not so many, but a handful of them, beginning from that time when structures have appeared. So we had to understand something about this receptor, and the first thing was a detailed comparison of closed and open structures, or what is the difference between them. The second thing was to simulate the thermal sensitivity and try to reproduce activation of the channel by heating the system inside the computer, you see, and finally to discover some driving forces of this thermal activation. What do you see here is a screenshot from our model, from our molecular dynamics system, which contains a receptor which is which consists of 4 monomers and a piece of biomembrane. This is the central part of the receptor. You see superimposed blue and red structures, and this is only the pore region. Red structure is open state, and blue structure is closed state. And here is the surface which shows the pore itself. And you see that in closed structure, the pore is closed in two regions, in the region of so-called upper gate and lower gate. Other domains of this receptor, which consist of S1, S4 helices, are not shown here. They should be somewhere aside. And one interesting method that we used to study this receptor was mapping of the pore. So the pore was, we were thinking about the pore as some space which is around a cylinder in its shape, but it might have some empty space inside it. And after that we performed a cylindrical mapping of this space. So this is the void space inside the open channel. You see that this surface is
continuous.
It is continuous from the very top to the very bottom, and in the closed state, which is to the right, we have breaks here. So somewhere inside there should be some barriers which cannot be overcome by ions and solvent and other things. So we just immediately see that there is a so-called two-gate mechanism, and at the level of the upper gate we have a filter, and at the level of the lower gate we have an interesting feature which might be called as a hydrophobic belt. There is a level where the pore becomes extremely hydrophobic, and it was an interesting thing for this channel. We performed a very big amount of computation. I will not talk about all of this, but there were many trajectories which length was from 500 to 1000 nanoseconds, and total exceed 10 microseconds. And the most essential thing about it that we performed calculation at different temperatures. Temperatures that were below the activation threshold of this receptor, and temperatures that were above. So there were cold and hot temperatures. And one thing that we have seen that S1, S4 domain was relatively stationary, that the receptor didn't fluctuate there. The main fluctuations were in the pore domain. And the most interesting thing was that we have seen opening of the channel when we heated the system inside the memory of the computer. These maps show the radius of the pore mapped during the time of molecular dynamics. And where you see the black band, it means that pore is closed, and where the black band is switched to a lighter thing, it means that the pore opens. And we have observed several examples of pore opening at the level of the upper gate and the level of lower gate. But another interesting thing is that the channel didn't close when we cooled down the system. So this was some sort of asymmetry in time, and probably receptor have larger time to get closed. Next, we have discovered that the opened pore is more hydrophobic than the closed one. So when the channel opens, it exposes additional hydrophobic surface to the solvent, to the pore. And this should have very interesting thermodynamic considerations because this increases heat capacity and also entropy of the system. And this effect might be at least partially underlying the temperature sensation effect. At the level of the upper gate, we have discovered that residue methionine 644 was the main moving residue which blocks the pore, and when it frees the pore as well when the channel opens. And the opening is asymmetric process, so not 4 subunits at the same time open the way for ions and the solvent, but this is just the single subunit which goes from the way and opens the way for ions and water, and others should open later, I suppose, but we didn't observe that event. The mechanism of pore opening was called piston-like mechanism because some segment of the channel was moving like that and freeing the way, and other movements inside of the receptor were observed, and they were highly correlated and opening the channel. So the main conclusions are that our computations have revealed temperature sensation effect in this channel, that opening of the upper and lower gates are independent from each other and are asymmetric in time and in space. At the level of the upper gate we have a so-called piston-like mechanism, and at the level of the lower gate we observe correlated motion of S6 segment and bending of TRP domain. Well, I didn't show the picture, but I didn't have to because I don't have time for this. This work was recently published in Scientific Reports journal. Thank you for attention.
I think he first made computations to decide how much time he needs for presenting his work, so he was excellent with the time presentation. Questions, please. Пожалуйста.
У меня такой вопрос. Значит, у вас там 500 наносекунд, да?
Ну, там было на самом деле
Симуляция.
более 10 траекторий, каждая из которых по 500 и 1000 наносекунд.
Среднее время пребывания иона в этом канале порядка 1 микросекунды. Значит, что вы в этом случае симулируете? Усреднение по времени, мне кажется, недостаточно в этой ситуации. Сколько бы траекторий достигали?
Я с вами согласен, что для изучения прохождения ионов лучше увеличивать статистику, с одной стороны, и мы это делаем, есть траектории более длинные, но я сейчас не говорил про ионы.
И второй момент. Значит, вы взяли только пору фактически. Значит, температурные скачки прилагаются ко всей молекуле. И как релаксировать температурное напряжение по всей молекуле, вообще говоря, не ясно. Поэтому критически здесь является как вы симулировали скачок температуры в вашей модели.
Ну, на самом деле, я, наверное, недостаточно понятно выразился. Мы взяли не только пору, мы взяли рецептор без 2 цитоплазматических доменов, без анкеринового повтора и без С-концевого повтора. Но все, что внутри мембраны, присутствовало целиком, включая большую петлю между 3-м и 4-м сегментами, кстати говоря, которые отсутствуют в экспериментальной модели. Мы ее реконструировали, и это был довольно важный момент, потому что многие данные говорят о том, что она важна для температурной чувствительности. А температура прилагается не только к рецептору, она прилагается и к растворителю, и к мембране, которые присутствуют в системе, и таким образом все это вместе нагревается и дает эффект. Но, с другой стороны, я с вами согласен, что те домены, которые мы опустили, тем не менее какую-то роль могли играть. Но мы наблюдали конформационный переход, и это была воспроизводимая вещь.
The last question, please. Okay. The 3 last question, and then the last one.
I didn't understand. You said that the gates, you only see one gate opening, one or the other. But you assume the other one opens as well. But how do you know this? I mean, if you see one open, then you already see a conductor change.
We have observed that upper gate opened and lower gate opened too, but twice less frequently as upper gate. so there should be some difference in the activation energy probably. The thing I was also talking about is that opening is not symmetric. So you do not have opening like this, but maybe like this, like this, like this, sequentially.
But is it responsible for the conductance or not?
I think this should affect conductance, but we didn't measure conductance because there should be considerable ion flow to measure this conductance. It was just a geometrical measurement of openness or closeness.
Your question, please.
Could you speculate why there's two gates and then they are not regulated at the same time, so they are independent of each other? What could be the reason for this?
Well, I'm not sure about this, and maybe someone else who is more deep in these receptors should answer a question, but I think this should be the reason of their multimodality of their action. They are very finely regulated by many different stimuli, and there should be different points of action, because if there would be just one of them, there would be not, they would not be that multifaceted as they are.
You have a question?
You did not look for the effect of pH on
No, no. It was just temperature effect.
Well, we have a wonderful talk and exciting and stimulating questions, but still we have to proceed, Ferdinand, and our usual
Okay, our
work with
next
the-
speaker is Dr.